AC 111, Lecture 7, Set 2, How to Design Finite State Machine in System Verilog. Let's start with a simple example, how we divide. We do a circuit for divide by n. What this means is that, we have a circuit that has a clock coming to it, and then every nth clock bit, we will have a pulse going on saying, this is the nth count. So in effect, it's dividing what is coming from the clock into 1/n of the frequency. So it's kind of a divide by n circuit. What is the input? Basically, since all the registers in the circuit are already connected to the clock, basically there is no input. And the output is just like, the pulse, which is like a 0, 1. So the output, again, is kind of a 1 bit where this output will be high. Let's go through an example in System Verilog how we express this and tell the hardware design language how this looks like. So for that reason, let's just focus on a simple divide by 3 example. What happens here, let's just go design, a simple finite state machine. This is like a reset state S0, where we come and remember, it's a good practice to always have a reset state for your finite state machine. Otherwise, you may get stuck in a loop that goes forever, and that's not recommended. So what happens is, we are going to get a clock tick. We're going to go to state S1. We're going to get another clock tick. We're going to come to state S2, in which case, the output here is 0. The output here will be 1. And then after that, we're going to go back to the original state. So this is a finite state machine with 3 states. Let's see how we define this to System Verilog, how we define this circuit in code. Here I'm showing just a waveform of the divide by 3 example. In System Verilog, what we are going to do is we are going to keep that finite state machine that we had in the previous page with 3 states. We are going to keep that in a parametric format. So let's just define parameters S0, S1, S2. We could give it initial values, but those initial values typically don't mean much to the synthesis tool. Now, because we had 3 states, that means that we, again, like the snail example we just had, the 3 states, we need 2 flip-flops to keep that to keep the state. So basically, we encode the parameters for the states like that. And now, in order to express to System Verilog, we have a finite state machine. There is a template, and I like that because that will keep things clear for me. And the template is kind of following what we had in terms of a million more state machine. Remember, we had that block diagram which said, your next state logic is going to come from the current state in the registers, the inputs applied that gives an input function, and then the states are going to go through a function which is a combinational to generate that output for us. So let's just divide it like we said. Let's just in terms of the divide by 3, we only have the it's a very simple circuit. So let's just think about the flip-flops. The flip-flops are basically expressed here. We have the always _FF, the command in System Verilog, and this is just defining for us the flip-flops. And it's going to just say, in this flip-flop we have a state variable, and the state variable, as we mentioned earlier, we needed 2-bit state variable was enough. So we define this state as a 2-bit variable, and naturally, if we have 2-bit variable, the next state will also be the 2 bits. Now, once we have that, we define a next state logic, which is a combinational logic, and a very common way to determine to express finite state machine in combinational logic is to use conditional statements using case or if then else. In this particular case, we are using you're using the case statement, and how it works is that, if you're in state S0, basically exactly this finite state machine. If we were in state S0 and we got, the clock comes, then you go to state S1, then, the next clock cycle we go to S2, and then we come back. So here is like really a very simple expression of that. And we have a notion of a reset state. So basically, it's the default here. So the default is going to say what would be, your next state. And the output is just basically if the state, the output state is S0, it's going to assert a signal that it is, the divide by n has got to the current state. Now, let's go to another example. This example is a little bit different from the one we originally saw. So in the first one, we saw like a finite state machine that we designed, and we kind of went and translated it into system Verilog. But if you have written good system Verilog code that has this combinational and sequential values separated, you should be able to even reverse engineer it and think what was, the state transition or the logic table used for making this. And this is just a simple example of that. So here, again, what happens is that we have a state and next state variables that are 2 bits, and we have 4 states. So if we were to make, the finite state machine, then we have just, these 4 states. In this case, S0, S1, S2, and S3. And the reset state here is the state S0. And now what you see here is just a case statement that comes, in a combinational format. So again, the combinational circuit is usually, if you remember those arrows going from one state to the other, typically it says, if you are in this state and this input comes, then you do this transformation, you go to the next state. And this is basically what it is. So here what it says, if it says if A or B is true, then if you're in S0, the next state will be S1. So if A or B is true, if you're in this, if not, basically not A or B, we stay in the same state. And the same, you could basically reverse engineer these. So from S1, we go to S2 if A and B is true. And if not, you go to S0. So this is basically not A and B. And same is true for all of these. And then Y is like, some kind of logic of this. So if you have written a good standardized finite state machine, you could always go back and do this, calculation in reverse. And people who see your code, they would be really able to understand what you have been trying to do and what your state transition graph was implying. Here's another example of finite state machine. Assume that we are designing a finite state machine that turns the first one in a string of consecutive 1s to 0s. So assume that, for the purpose of this problem, let's assume that in each clock cycle we have one input arriving. So our input is basically 1 bit. And the output is just going to 0 the first one in a string of consecutive 1s. So here we see a 1, it turns to 0, 0, this one will be 0, 0, 0, 0, and here we have 1, 1, 1, so the first one turns 0, but then the next ones are going to remain 1, 0, 0, again, the first one is going to go 1, and so on and so forth. So the question is, how many states do we have for this? And there are many ways to design this. You could say, you could design this, I have a I am in some state and I'm seeing a 0. So my output is 0. I'm in some state, I'm seeing 1. And now the question is, which one is that? Is that this one, which is the first in the sequence, or the second one, or the third one in the sequence? Does it matter if it's the second one or third one? Not really, but it matters if it's the first one. So let's just have this distinction that, I'm in a state where I have not seen A1. Then another state would be I have seen a single one. And then, the third one is I am in, basically I am in kind of the sequence, in a consecutive sequence of ones, in the consecutive sequence of ones, or I have seen, or have seen more than a single one. So let's go and think about the finite state machine in this particular case. So if I'm in a state S0, which I assume that is also the reset state, what happens if I have I'm in state S0 and I get a 0? I'm going to stay here. So the output will be in S0. The output will be 0. If I get a 1, what will happen is I'm going to state of the second state, which is where I'm seeing a single one. But then, in state S1, also what I'm going to output is another 0. But then if I get a 0, I'm going to come back to the state. But if I get a 1, I go to this third state where I'm in a sequence of ones. So this is basically S2. And if this is the case, my output will be 1. And here, what happens if I get a 1, I'm going to stay in this state. But if I get a 0, I'm going to go back to the state. So now that we've designed the finite state machine, let's see how this thing looks like in system Verilog. Here I have on the slide the same thing I just drew on the board. What we will see here is that, if we have this 3 states, we could use parameters, and, because it's 3 again, we can use 2-bit to define 3. And this is a symbolic statement. So the initial values that I assign to the states are, basically are not going to be interpreted exactly by the synthesis tool. The synthesis tool may optimize and use its own values for coding that. But if you're trying to code things, try to make it standard. So when you're talking about registers and assigning values to the registers, use non-blocking. When you're trying to do a combinational circuit, then use blocking. And that way you kind of make sure that you get the correct functionality out of this. Again, we have the finite state machine. Here, what we do is we define, the state register, which is a 2-bit, and we have the parameters which define states S0, S1, and S2 as shown on this finite state machine. And then, if you're in a reset state, we are going to get, we're going to stay in state S0. And then what happens in this state is that your output is going to be 0. So the output is Q here. And now, if you're not in the reset state, what happens is that we want to just tell this code word by word how this finite state machine works. And this is done in this case by a case statement. So if your state is in S0, what happens is that, if we get a 1, we are going to go to state S1, and the output here will become 0. If not, we are going to go to, from S1, we are going to go to state S2, and then you could also you could continue doing that, and then you could continue defining these connections here, which is done in this code, and then you could continue defining your finite state machine in Verilog. Next, we will be talking about another example in finite state machine.